Riemann sums and definite integral.
Riemann sums and integrals are motivated by problems in physics and geometry. For example, suppose we have this velocity curve. How to find the distance traveled in the first 4 seconds? We know from physics that our displacement is the average speed times the time, but our velocity curve is nonlinear. At first it's increasing very fast, then it's increasing slower. So how to find the average velocity for such curve? A naive approach is to sample the velocity at regular time intervals, say every millisecond, and then we would take the average of our samples. Would we always get a good estimate of the displacement this way? It turns out that if the velocity function is continuous, then our approach of sampling the velocity at regular spaced intervals works just fine, and the more often we sample the velocity, the more accurate estimate of the displacement we are going to get. On the other hand, if the velocity curve has many jumps, then sampling at regularly spaced times might be too restrictive and lead to potential errors. So we are going to specify a more general sampling procedure and to describe the class of functions for which that sampling procedure leads to accurate computation of the displacement. Here is the general setup for defining Riemann sums. Suppose we have a function defined on the x interval from 1 to 7. More generally, it's going to be x interval from x equal a to x equal b. So we are going to divide our x interval into n smaller intervals of equal lengths. So the length of each interval will be the total length, which is b minus a, divided by the number of intervals. So that length of individual intervals is traditionally denoted by delta x. On this picture, we have 3 intervals. So we divide the interval from 1 to 7 into 3 intervals. The total distance from 1 to 7 is 6. And if we divide 6 into 3 equally spaced intervals, we get that each interval will have length 2. So in our case, delta x equal to 2. Okay, so now let's look at the partition points. Okay, so we start from the leftmost point, x0 equal 1. Then we travel 2 units to the right. So the new point is x1 equal to 3. Then we travel another 2 units to the right, and we get the new partition point x2 equal to 5. And 2 more units to the right, and we arrive to the final point x3 equal to 7. Now on each of our intervals, we choose a sample x value. Let's denote them by P1, P2, and so on, Pn. On our picture, where we have only 3 intervals, we have sample x values P1, P2, and P3. Those sample x values can be positioned anywhere inside of their intervals. Now we compute the y values at each sample point P1, P2, so on, Pn. And we take the average, which we denote by y bar. If we interpret f as a velocity curve, then y bar would be simply the average velocity. And just like the distance traveled is the average velocity times the time length, we are going to define the quantity, the average y value that we just computed, times the total length of our interval AB. And we call this Riemann sum. So the Riemann sum will be the product of b minus a times the average y value. Now note that we have summation of the y values multiplied by the term b minus a over n. But b minus a over n is just the length of each individual interval, which we denote by delta x. So we can write our Riemann sum as summation of the sample y values multiplied by the length of each individual interval. This sum has a simple geometric interpretation. The product of the sample y value and the length of the interval can be interpreted geometrically. So the sample y value, for instance, here we have the sample y value f of p1 multiplied by the length of the interval, we can interpret as the area of the rectangle whose base is the first interval and whose height is given by the sample y value. Note that on our picture, the last sample y value, f of p3, is negative. So the term f of p3 times delta x will be interpreted as this area, but taken with negative sign. So we have area 1 plus area 2 and minus area 3. Here's an example. We are given the function square root of x on the interval from 0 to 3, and we need to write the Riemann sum using 4 intervals and the sample points given on the picture. First of all, the distance between 0 and 3 is 3 minus 0, it's 3, and we divide into 4 intervals, so delta x is 3/4. Now we are ready to write the Riemann sum. So at each of these sample p points, we compute the square root to get the sample y values, and then we multiply each sample y value by delta x, which is 3/4, and add them up, and we get the Riemann sum. We can write the Riemann sum for any value n, where n is the number of intervals, and for any choice of sample points. Now, just like for estimating the distance traveled from the velocity curve, the more frequently you sample the velocity, the more accurate you get the result for the distance traveled. Similar, in many other applications, we are interested in sampling the y values frequently to improve the precision of the quantity represented by the Riemann sum. So we are interested in what happens with the Riemann sum when n, the number of intervals, is becoming large. And if all Riemann sums, no matter what sample points you choose, are approaching the same number when n is becoming large, then we call that number a definite integral of our function between x equal a and x equal b. So one more time, the limit of Riemann sums when n goes to infinity, if it exists, is called the definite integral, and this is a notation for the definite integral. So what are the elements of this notation? The first symbol, it's called integral sign. It actually originated as a Gothic letter S, referring to the fact that in Riemann sum we were doing summation. Now, inside of the integral we have f of x dx. So this resembles what was in the Riemann sum, the sample y value times delta x. I recall that the founders of calculus were regarding dx as an infinitesimally small delta x. So, when n goes to infinity, the length of each interval delta x becomes extremely small, and they were writing it as dx. Okay. Now, the integration is from x equal a to x equal b. These two numbers are called lower limit of integration and upper limit of integration. The word limit here has nothing to do with limits from calculus 1. These are just boundaries of our interval AB. Geometrically, what does the definite integral represent? Recall that a Riemann sum is the sum of areas of rectangles like this above x-axis minus areas of rectangles below x-axis. As n goes to infinity, the sum of the areas of rectangles above the x-axis will approximate more and more closely the total area under the curve. Similarly, the sum of the areas of rectangles below x-axis will approximate more and more closely the total area below the x-axis but above the curve. So the definite integral is the total area above x-axis minus the total area below x-axis. Now let's look more closely on this limit. So in order for this limit to exist, all Riemann sums for any choice of sample points must get close to the same number whenever n is sufficiently large. Computing such limit directly is a laborious task. Luckily, there are alternative fast techniques for computing definite integrals. However, we still need to learn Riemann sums because we are going to use them in applications in order to set up a definite integral. Let's summarize the geometric interpretation of the definite integral. So if the function is above the x-axis, then the definite integral represents the area under the curve. If the function is below the x-axis, then the definite integral represents the area between the x-axis and the curve taken with negative sign. And in general case, if part of the curve above x-axis, part is below, the definite integral represents the total areas above x-axis minus the total areas below x-axis. In business math, this is often interpreted as gains minus losses. Does the limit of Riemann sums always exist when n goes to infinity? Not always. That depends on the function. We say that a function is integrable if all Riemann sums for all choice of sample points would converge to the same number L as n goes to infinity. Are there any functions which are not integrable in this sense? Here's an example. Suppose we have a function which is 0 at the origin and it is equal to 1 over x for positive x. So we claim that this function is not integrable on the interval from 0 to 1. That's because for a fixed value of n, no matter how large it is, we have a freedom to choose the sample points inside of each interval any way we like. In particular, we can choose the first sample point to be as close to 0 as we like. And this way we can make the corresponding sample y value, the first sample y value, as large as we like. This way we can make the average y value of the sample points to be as large as we like. So we can make so some Riemann sums for a fixed n are going to be very, very large. So even though n goes to infinity, there is no way we can restrict the size of Riemann sums simply by making n very large. The good news is that continuous functions are always integrable on a closed interval. This is not entirely obvious, as continuous functions can be fairly complicated. For instance, here's a function which, as x approaches 0, is oscillating faster and faster, but it's still continuous. So the integral of this function on closed interval, for instance, from 0 to 1, would still exist. The proof of this theorem is non-trivial and is discussed in more advanced courses. In applications, we'll be mostly dealing with functions that are either continuous or consist of a finite number of continuous pieces. One corollary of this is that if you know that a function is continuous, we don't need to verify that it is integrable because we already know. Moreover, to compute the integral as the limit of Riemann sums, we don't have to regard all possible Riemann sums for all possible choices of sample points. We can just look at some choices of sample points. For instance, we can focus only on those Riemann sums where the sample point on each interval is chosen to be the left point of that interval. So, for example, let's look at this picture. On the first interval between x0 and x1, we choose the sample point to be at the very left, so it would coincide with x0. For the second interval between x1 and x2, we would choose the sample point to coincide with the leftmost point, so with x1. And on the last interval, the sample point would coincide with x2. So the Riemann sum in this example, f of p1 times delta x plus so on plus f of p3 delta x, it will be f of x0 times delta x plus f of x1 delta x and plus f of x2 delta x. And more generally, if you have n intervals, you can write such, we call it a left Riemann sum, as summation from the index I equals 0 to the index n minus 1 and the summation of the terms f of xi delta x, where xi are the partition points. So if you already know that the function is integrable, then we can only focus on like specific type of Riemann sums, like in this example on the left Riemann sums, and take the limit of those. This often leads to simpler calculations. Let's do some examples of computing definite integral. So first example, suppose we have a linear function y equals 3x, and we want to compute the integral from 1 to 5. And since we can interpret this integral as the area under the curve, and the curve is a straight line, we recognize that the region under the curve is a trapezoid. And we know how to compute the area of the trapezoid. It is the average height of the trapezoid, so in our case it will be the average of 3 times 1 and 3 times 5. So it will be 3 plus 15 over 2. And multiplied by the length of the base, which is in our case 5 minus 1. So we have the average of the y values at the endpoint multiplied by the length of the interval. So 3 plus 15 over 2 times 4, which is 36. Now let's do the same problem, but using Riemann sums. In particular, let's try to use right Riemann sums this time. Okay, so we have interval from 1 to 5. We partition it into n intervals. What will be the partition points? So we start with the leftmost point 1. We travel delta units to the right. So the first partition point will be 1 plus delta. Then we travel delta units to the right again, and we get the next partition point 1 plus 2 delta, etc. The last, until we arrive at the very end, since we have n intervals, that means that we travel delta units to the right n times, so the last point is 1 plus n times delta. Now, on each interval, since we want to use right Riemann sums, on each interval, we are going to use the rightmost point of that interval. So on the first interval, we are choosing the point 1 plus delta. On the second interval, we are choosing the point 1 plus 2 delta, etc. On the last interval, we are choosing the point 1 plus n delta, which is the same as 5. So these are our sample x values. Okay, so we got the sample x values. What about their y values? Since we have the function y equals 3x, we multiply each x value by 3. Now, so here we have sample y values. Note that they form linear progression, linear or arithmetic progression. That means that when you go from one y value to the next one, the y value increases by the same amount. In this case, it increases by 3 delta. Okay, so to get from the first y value to the second y value, you add 3 delta to the first y value. Then to get the third sample y value, you add 3 delta again, and so on. Now, since the y values form a linear or arithmetic progression, we know how to compute the sum of such y values. We just need to add the first y value and the last y value and divide by 2, so take the average and multiply by n. This is the same as when we studied series, when we were adding 1 plus 2 plus 3 plus so on plus 100. Okay, the same idea. Now, let's recall that delta. That's the total length of the interval from 1 to 5, so 5 minus 1, divided by n. Okay, so n cancels, and we get the formula. So it is half sum of f of x1 and the last y value, which coincides with 5. So it's half sum of f of x1 and f of 5 multiplied by the length of the interval. Now we take the limit of the Riemann sum as n goes to infinity. Equivalently, since the length of each interval is 5 minus 1 over n, as n goes to infinity, the length of each interval goes to 0. So equivalently, we can take the limit as delta goes to 0. So note that as delta goes to 0, the first partition point that appears in our sum, it approaches 1. So the Riemann sum, x1 approaches 1. So the Riemann sum approaches the half sum of f of 1 and f of 5 times the length of the interval. So the value of our definite integral is given by this formula. Note that this is the same formula that we obtained when we were computing the definite integral by interpreting it as the area of a trapezoid. Another example. Let's compute the definite integral of the exponential function 2 to the x from x equals 0 to x equals 1. Let's try to use left Riemann sums this time. So, first of all, we partition the interval from 0 to 1 into n equally spaced intervals. So, the length of each interval is 1 minus 0 over n, so 1 over n. And let's look at the partition points. So, we start from 0. We travel delta units to the right, so the first partition point is 0 plus delta, then another delta units to the right, we got 0 plus 2 delta, then 0 plus 3 delta, and so on. Okay, so we are going to compute the definite integral by taking the limit of the left Riemann sums. So in the left Riemann sums, the summation is from I equals 0 to n minus 1, of the terms f of xi times delta. Now, what is f of xi? So our xi is simply I times delta. We plug it into function 2 to the x, so we replace x with I times delta. So we have 2 raised to I times delta. Now let's recall that when we have product of two powers, it's the same as 2 raised to the delta and all that raised to the I. Now observe that our sample y values are actually forming a geometric progression. 2 delta raised to the 0 power, which is 1, 2 delta raised to the first power, 2 raised to the delta raised to the second power, and so on. So it's a geometric progression. To get from one term to another, to the next one, we multiply the previous term by 2 raised to the delta. Now let's recall the formula for the sum of the first few terms of the geometric progression. 1 plus r squared plus so on plus r raised to n minus 1. That's 1 minus r to the n divided by 1 minus r. In our case, r is 2 raised to the delta. So our Riemann sum, which is geometric progression, we can pull delta outside of the sum, and the summation of these power terms, it will become 1 minus r to the n, so 1 minus 2 raised to the delta to the n, divided by 1 minus 2 to the delta. Now let's look at this term 2 raised to the delta and then to the n. We can simplify it. 2 raised to the delta and then to the n. Let's recall that delta is just 1 over n. So we have 2 raised to 1 over n and all this raised to the n. So it's the same as 2 raised to the product of 1 over n and n. N cancels, so it's the same as 2 raised to the first power. So this expression can be simplified. So the numerator is just 1 minus 2. Now, delta divided by the denominator, when you want to take the limit as delta goes to 0, this will actually be the limit of 0 over 0. And we can take this limit by using L'Hopital rule. So we take the derivative of the top and the bottom with respect to delta. So the derivative of the top is 1, the derivative of the bottom, derivative of 1 is 0, derivative of the exponential function with base 2 is the exponential function itself times natural log of 2. So we applied L'Hopital rule. Now we try to take the limit again. 2 to the delta approaches 2 to the 0, which is 1. So we have 1 divided by minus 1 times log 2 and times 1 minus 2, which is negative 1. So we got the final answer, 1 over log 2. Again, this method is laborious, and later on we'll learn much faster methods for computing definite integrals. But we just wanted to get a general idea what it takes to compute the definite integral from the definition. One of the most popular function in calculus is the power function. How would we compute definite integral of power function? How would we do it from the definition using the Riemann sums? Here is one useful fact that will help us to compute integrals like this from the definition. If you have summation, let's suppose that p is some positive integer, and we want to add 1 raised to the p plus 2 raised to the p plus so on plus n raised to the p. Is there some simple formula for this? It turns out there is. This sum can be written as the following polynomial. The leading term will be n raised to p plus first power divided by p plus 1, plus some polynomial of the form c0 plus c1n plus c2n squared plus so on plus cp n to the p. Now, the exact form of that polynomial is not really important for our purposes of computing integral. We are really interested in the leading term. Now, here's an example. So 1 square plus 2 square plus so on plus n square. There is actually a simple formula for this. Well, maybe not too simple, but a finite formula for this. And if you FOIL all these terms, you will see that this is actually a cubic polynomial. The leading term, so how would you compute the leading term? 2n over 3 times n over 2 times n. So it will be 2n cubed divided by 6, which is n cubed divided by 3. So the leading term of this polynomial is n cubed over 3, and the rest of the terms, they will have smaller powers. So c0 plus c1n plus c2 and n squared. We'll revisit this fact and discuss the proof at the very end of this lecture. Here is an example. Let's take the function f of x equal x cubed. So suppose we want to compute the area under x cubed from x equals 0 to x equal 1. So let's use Riemann sums for computing this integral. We have interval from 0 to 1. So we divide it into n intervals of length delta. So we start from x equals 0. We travel delta units to the right. So the first partition point is delta. The next partition point is 2 delta, then 3 delta, and so on. And since we are using the right Riemann sums, our sample points are going to be, so for the first interval, we select the rightmost point. The interval is from 0 to delta, so the rightmost point is delta. That's our first sample point, P1. On the next interval, the rightmost point is P2 equal 2 delta. On the next interval, P3 is 3 delta, and so on. Now we are ready to write the Riemann sums. So once again, our delta is 1 over n. The sample x values have the form I times delta. And our right Riemann sum, the summation starts from I equal 1 to n. Now, inside the summation, we have the sample y values times delta. To get the sample y value, we plug in the sample x value I delta into our formula for our function. So instead of x, we put I times delta. So the sample y value is I times delta cube. And since we multiply by another delta, the total power of delta is the force. Now, delta, it does not depend on the index of summation I. So we can pull delta raised to the fourth power outside of the summation. So we have only I cube inside of the summation. So we are adding 1 cube plus 2 cube plus 3 cube plus so on plus n cube. And let's recall the formula for such sum. So it will be a polynomial of the fourth degree. So it's n to the fourth power divided by 4 plus terms of lower powers, c0 plus c1n plus c2n squared plus c3n cubed. Now, our sum is multiplied by the fourth power of delta. And delta is 1 over n. So our polynomial is multiplied by 1 over n to the fourth. And so the leading term, in the leading term, we have cancellation. N to the fourth cancels with n to the fourth at the bottom. As to the rest of the terms of the polynomial, when we divide by n to the 4, we'll get negative powers of n. So our Riemann sum is 1/4 plus combination of negative powers of n. Now, in order to compute the definite integral, we need to take the limit as n goes to infinity. The terms with negative powers of n are going to 0. So the only term that survives is 1/4. So our definite integral equal to 1/4. Here are the main algebraic properties of definite integral. So first of all, if you take a definite integral from a to b and add a definite integral from b to c, it's the same as a definite integral from a to c. If the function is above x-axis, this is actually obvious because it says that the total area of two non-overlapping regions is just sum of its parts. However, this property remains true even if the function f is not necessarily positive. And the reason is the following. If you take a partition of the interval from a to b and a partition of the interval from b to c, and we regard those two partitions together, it will be partition of the entire interval from a to c. And if we add two Riemann sums, one from interval AB, another from interval BC, it will be a Riemann sum for the entire interval AC. For the next property, first let's recall that when we introduce definite integral, we always assume that the lower limit of integration is smaller than the upper limit of integration, so a smaller than b. This limitation can be inconvenient sometimes when a and b are not just constants, but some expressions that involve a parameter. So let's extend our integral to the case when the upper number is actually smaller than the lower number, like integral from 2 to 1. We want the additivity property to always hold. In particular, we want, for instance, integral from 1 to 2 plus integral from 2 to 1. According to this additivity property, we want it to be the integral from 1 to 1, but integral from 1 to 1 is 0 because it just represents the area of a region of width 0. Okay, so integral from 1 to 2 plus integral from 2 to 1 is 0. Therefore, integral from 2 to 1 is minus integral from 1 to 2. And more generally, integral from a to b is minus integral from b to a. The next algebraic property is when we have a definite integral of an expression like sum of two functions or difference of two functions. In that case, the integral can be split into two pieces, integral of the first function f and integral of the second function g. To prove this, we again need to look at the Riemann sums, so we are going to leave this as an exercise. Here's another useful property. If we have two functions f and g, and if function g is always above the function f, then the integral of g is greater or equal than the integral of f. To prove this, we again need to look at Riemann sums, but if f and g are positive, intuitively we can interpret everything in terms of area. The higher the function, the larger the area underneath. This property is actually quite useful when we need to quickly estimate how large the integral is, and the function inside of the integral is fairly complicated. For example, let's look at the definite integral from 0 to 3 of 1 over 5 plus cosine x. This function 1 over 5 plus cosine x is fairly complicated, and computing such integral can be difficult. But we can make a quick estimate to get some estimate from above for this integral. First observe that cosine at the bottom is between -1 and 1. So the smallest value that this cosine can take is -1. And the smaller this cosine, the larger the overall fraction. So the largest value of this fraction would be when cosine is equal to -1. So we have an overestimate of this function by 1 over 5 minus 1, which is a constant. It's just 1/4. Okay, so our function inside of the integral is less or equal than 1/4. Therefore, the integral of our function is less or equal than the integral of the constant function 1/4. Then the integral of our function, represented by the area under the curve f, is less or equal than the integral of the constant function 1/4. And that integral we can compute from geometric consideration, since it represents the area of the rectangle of the height 1/4 and the width 3. We have 1/4 times 3, which is 3/4. So our given integral is less or equal than 3/4. Finally, let's revisit the formula for the sum of squares, 1 square plus 2 square plus so on plus n square. How to derive a formula for such sum? One preliminary idea, let's regard each term in the sum. So each term has the form k square. So we regard it as an y increment of some function f. We know from calculus that x square is derivative of 1/3 x cubed. So we think about k square as derivative with respect to k of k cubed over 3. And the derivative is approximately the rise over run. Let's take the run to be 1. In that case, the rise is just the difference between two consecutive values of k cubed. So k cubed minus k minus 1 cubed. This is just an approximation, so this is a very rough idea. We still need to fill in the details. Now, okay, so we interpret k square as approximately difference of k cube and k minus 1 cube divided by 3. Now, when we add 1 square plus 2 square plus so on plus n square, we are adding all such increments of the cubic function. When you add the y increments of a function, you get the total change of the y value of that function. It's the same idea that you see in telescopic sums. So when you add the left, when you do the summation, so you add k cubed minus k minus 1 cube for different values of k, you are left with n cube minus 0 cube, the total change in the cube function. And we still have 1/3. So we have this approximate identity. In what sense approximate, we'll see in a moment. So now let's fill in the details. First, if we FOIL k minus 1 cube, we'll get k cubed minus 3k squared plus 3k plus 1. The difference k cubed minus k minus 1 cube, k cubed will cancel, and you will still have the combination of 3k squared, 3k and 1. So k cubed minus k minus 1 cube is 3k squared minus 3k plus 1. We want to isolate the term k squared. So first we move 3k plus minus 3k plus 1 to the other side, and we divide everything by 3. So we get the following identity. And now let's do the summation
For all k from 1 to n.
So the left side would become 3 times 1 square plus 2 square plus so on plus n square. As to the right side, so when we add all the increments of the cubic function, we get the total change of the cubic function, n cubed minus 0 cube. Now, as to the other term, as k runs from 1 to n, the terms 3k minus 1, they form a linear progression. And we know how to add terms of a linear progression. It is the average of the first term and the last term multiplied by n. Now we simplify the numerator in this expression and we get a quadratic polynomial. This completes the proof.